Welcome to BS Explained. In this video, I'll demonstrate you how to select a control valve and its actuator, and let us see what are the different types of valves and actuators you have and what are those applications used in. So, in this video, I have divided the whole video into 5 sessions. So let us go through what and all we'll see in this video. Session 1 would be understanding what data you should be looking into when you refer to a mechanical drawing to select a valve. What are the critical data? Session 2 will be what type of valves and actuators you'll be selecting and based on what application you'll be selecting and why do you have to select and who tells you to select that, or why do you have to specifically select what actuator based on the jobs. That be session 2. Session 3 would be understanding the selections and the parameters what you have selected, what are the critical parameters while selecting, and how does that impact of your selection and the job itself. And session 4 will be understanding the differences between data when it comes to imperial and metric units. So it differs from continent to continent. We'll go through that. And session 5 would be the conversion formulas which you'll be using and understanding those formulas, what you have used for your selection. So this is the whole video brief which we are going to go through. So let's dive into it. Alright, so the first session which I said what and all you need to understand when you have a mechanical drawing. The first and foremost thing which you need to see in a mechanical drawing is what are your line sizes going to the equipment. So based on your line sizes you will be selecting your valve size as well. So it differs from equipment to equipment based on their mechanical designs, how much of the flow is going, how much of the unit requires of specific flow, and that alters the line size as well. So your first and foremost thing which you need to get from the drawings is line size. The next thing which you want to do is get the flow data and pressure drop. So this flow data and pressure drop is usually tabulated in the schedule for specific equipments which you are selecting your valve to. So either you can go through your mechanical drawings for the flow data and the pressure drop, or this will be specified in the submittal of each and every equipment. So let's go and see if this is a mechanical drawing you have. So where are your line sizes? So you'll see a bunch of line sizes in a piping layout. Which one is that you should be looking out for specific equipment? So if the pipe which you're seeing here is having a 3-inch line, you don't select to a 3-inch line, but the one at the tail end which is coming to your equipment is your line size which you'll be selecting. In this case, if it is going to a VAV box as such, your line size will be quarter of my bad, 3/4. So let's take another example. So this here comes as a hot water pipeline, and this is a chill water pipeline. So this is 3/4 and this is 3/4 going to some other unit. So you have to consider a last end size which they have given. If in case they haven't given you the line size, there might be specific notes which should be telling you in the drawing that all the terminal units or the equipment which you're sizing to should have a note given or a specific line size given. If it is not given, you should get back to your mechanical people and get the line sizes clarified. So the next thing which we wanted to do is the flow rate and your pressure drop. So it is usually when they do an equipment based on the coil, you'll see how much the flow rate is across the coil going through the coil, and the maximum water pressure drop usually you'll see and these are given in specific units of themselves. So this flow rate is given in gallons per minute, and this is feet per H2O. So based on your schedule, what you're using, based on what you decide, or based on which valve you're using, you got to convert these and make it into a specific pressure drop which you're looking into. Alright then, so what do you do after selecting or after grabbing all the data from the mechanical drawings? So you gotta understand according to what applications which valves has to be selected. There are n number of valves which you can select in the control valves based on what applications you're using and which is apt for that application. So let's take a look at what are the types of valves you can get. Alright, so majorly in our controls we'll be using either a globe valve or a ball valve or a butterfly valve. Let's see what a globe valve is. So as you see, this is typically how a globe valve looks like. There is an inflow where it comes in, and you see this is a plug which goes up and down regulating the flow. So the water or a liquid, whichever is going through the valve, gets into this, and according to how much this plug is open or closed, the flow will be regulated on the other end. This is how a globe valve is used. And the next one would be a ball valve. So how ball valves use is the pipes are attached on the either end. So this is a ball which rotates 90 degrees either to either to restrict the flow or ease the flow. So if the ball is against the water coming in, it will restrict the flow on the other side. And this is the mechanism of how a ball valve is used. So the other one which we have, which is commonly used, is butterfly valve, which is usually used in larger applications when the when the line sizes are greater than 3 to 4 inches. So these have a flaps which goes against the flow when it is closed like this. When it opens, turns to 90 degrees, opens, it allows the flow. And there are mechanical installation differences between all these three valves, how it can be installed and such. We'll take a look at that later. But this is how the applications work, or this is how the valves work according to their operation. Mainly they get their names with respect to how their mechanical construction is. So this being having a ball inside for regulating the flow, it gets the name as ball valve. Alright, let's look at individual valves and its where the application is used in. So let's take a look at globe valve. So where are globe actually used? So globe is actually specifically used where there are modulating applications where you need to control a temperature with heating or cooling coil, where you need to modulate the water flowing through the coil. So this is majorly used for modulating applications. So as I said earlier, the plug closes against the flow to restrict the flow to the coil. So the applications using globe valve, it is commonly used while you want to modulate the temperature, as leakage in this thing is very minimum. The pressure drop across the valve would be not of a greater extent, which should be ideal for the modulating application. The only con, as with respect to the pros and cons, is the globe valves will have lesser close off rating. The close off rating is against your pump head, it has to, let's say, the flow has a specific pressure which is coming in, It has to withstand that specific pressure. That's the close-off rating. It has to, against the flow, it has to close its plug. So that's the close-off rating which we're talking. So globe valve usually have lesser close-off ratings. So when a ball valve is used, ball valves are usually considered for on-off applications, as the ball turns 90 degrees and eases the flow or restricts the flow when it is closed. These are usually not used for PID control or temperature control in an ideal selection, until and unless the customer asks you in the specification that they specifically want to use ball valve, maybe because of the pricing reason, maybe because of n number of reasons. So it depends on what manufacturer they're asking you to quote in. So those are all dependent on how the project need and requirement is. But the ideal applications which we should use ball valve is in on and off and not in PID. Next is the butterfly valve. These are used in on-off application as well. The installation is usually flange, which you see here. So this takes lesser space across the pipeline compared to the ball and the globe, as this is just a flat plate or flap which goes opens and closes for the flow. These have these are not really helpful for modulating applications, as these have a higher rate of leakage and cannot contain the pressure drop across the valve. So these are usually used for larger application when your line size is higher for on-off type. So these are all the types of valves which we can come across while you're going with valve selection in your day-to-day um, control applications. Okay, so what and all do you see while selecting a globe valve? Now that you have line size, now that you have flow data, pressure drop across the valve which is specified in a tabular column, you know, if you want to have a modulating type which is trying to control a specific temperature in a VAV box or in an air handler, so you have globe valves. What do you see? Oh, how do you select in the globe valve? Is it a two-way? Is it a three-way? Do you want it flanged or a threaded? How do you want the installation? So based on that, you can select the valves here, and based on the valve size, you can select in one of these and what has specified in the specification with respect to what his body should be, what his trim should be, uh, and what should be the answer rating or the close-off rating. Based on all of that, you contain all of this with respect to what actuators you should use. Should it be fail-safe or non-fail-safe, which is a spring return. When you lose power, it goes to a specific position, which are majorly used in safety purposes. Let's say in a heating application, you don't want your valves closed if you're bringing in 35 Fahrenheit of cold air into the coil. The coil might freeze up and burst. So you want to have a spring return actuators for such conditions. What kind of power supply do you need based on if you're using a 120 at your panel or directly feeding to the actuators, which electrical your subcon might give, you might say, I'm not providing 120, I will just provide 120 at your panel. Then you can provide a transformer and use 24 from your transformer to the actuators. So based on all of that, you can select whatever you need. This is a specific table which I've just grabbed from web. This is basically a Belimo actuator table which you can select from. I will get to what and all, how do you select the sizes. This is just to demonstrate what and all you go through while you're selecting a globe valve. In the same way, you have ball valve as well. So based on what your valve sizes is, you can go through different line size and valve size with specific CVs. So I'm gonna go across what CV and everything is, and then I'll come back to this slide again to show how it matters and how it goes. Alright, so what and all the process you go through for valve selection, and what and all parameters are very critical for that. Selecting a valve. Selecting a valve is nothing but, are you selecting a globe valve or a butterfly valve or a ball valve? That's your first step. Then, how much of your pressure drop should be after you select a valve across against what you have in the tabular column? How far can you go? How lesser than that can you go? Or how much more than can you go of what the maximum pressure drop has given in your tabular column for that specific unit? The next thing is, how much should your coefficient of flow be? Coefficient of flow is what something you saw earlier in the slide, which was CV. I'll tell you what the importance of coefficient of flow is after we go through the valve schedule. So let's go see a sample valve schedule in an imperial tabular column, which is given in the mechanical drawings. So let's say you have an air handler 1 which has a pipe inch of, or a line size of 6 inch, and has, this is just hypothetical, you don't have like just 20 GPM going through a 6 inch. So if you have 6 inch 20 GPM, and then the pressure drop which he has shown is 2.9, you should consider that this is delta P in PSI. What we saw earlier in the slide was feet H2O. You can easily go to web and access feet H2O to PSI conversion, and you'll get to know how you'll get to see how much of the actual value of feet H2O to PSI is. Let's say if the tabular column had 15 in it, and for feet H2O, if you convert it, it comes to around 6.5. So you should have your delta P as a maximum of 6.5, which should be designed. So delta CV is calculated based on your flow and your delta P. How is that calculated? Is from a formula which is CV, coefficient of flow, is equal to flow rate. So what is CV? CV is coefficient of flow coefficient, Q is flow rate, SJ is specific gravity of whatever liquid is going through the coil. Usually it would be hot water or cold water, which is specific gravity of water is 1, and delta P is pressure differential mentioned for the specific equipment. So you know how much your flow is, which is 21.3 in my case. Delta P is 6.5. So 1 divided by 6.5, the square root of it, and what you see is your CV here, 8.4. Now, how do you size your valve? Now, let's say if I'm going and selecting my valve to be a globe or a ball valve. So let's go back to PPT here. Let's select here. Let's say if you're selecting a 4-inch flanged wall with a valve size of 4-inch, and you can select CV of how much ever you have here, which should match 8.4. The nearest one we have is 7.5. So you select a CV of 7.5, and you'll see a pressure drop across this, which is 8.1. How is a pressure drop calculated again? From the same formula, by altering, you move your flow rate with your CV, which you have already with 7.5, and then do the pressure drop. Now you got your pressure drop, which is an actual pressure drop across the valve, and this is the pressure drop which he has given to you. 6.5 should be my pressure drop, and you have got 8.1. What is the next CV you have in your available here is 5.5. So I'm not going with an actual selection. These will alter a whole lot. So 5.5 cannot be a CV for a 4-inch valve. So this is just theoretical, which I'm giving to you with respect to what comes across. So let's say CV is 5.5 and your CV required is 8.4. Your pressure drop goes sky high to 15, which it should have been regulated at somewhere near 6.5. So CV is nothing but how much of the flow actually goes in with your pressure drop across the valve. If you're sending in 21 gallons per minute across the valve, so they are saying there should be a coefficient flow of 8.4, while across what you take in your valve it just goes still 5.5. So you always want to have higher CV to match what is calculated against your pressure drop given from the tabular column. So if the best guess would be 7.5 or 10, let's say if we put 10, you will see a pressure drop of 4.5 against 6.5, which is not bad. How do you know which is good and which is not bad? That is what the valve authority gives you. The valve authority is just nothing but the pressure drop across your valve with the sum of the pressure drop which is given in the mechanical design and the pressure drop you get, which should be in a range somewhere between 30 to 60. This is a specified region where you have a good selection of valve done. If you get the valve authority between these, then you have a very good valve. Let's say 10, if your pressure drop is, you're saying 6.5 is what's specified and 4.5 is way too low, go for 7.5 CV valve and see how much you get of valve authority. 55, which is on a higher side of 30 to 60, which you can use. The pressure drop is more or less more nearer to 6.5 rather than 4.5. And this is how you select a valve, be it globe or ball valve. The only difference in ball valve and globe valve is if you go to ball valve, you will see, let's say you have a line size of 3/4 and you're choosing a half size valve. So I'll show you this. Let's do another. Let's do 1 inch. So if you are selecting a 1-inch valve, a 1-inch line, you have a 1-inch line and you're selecting a 1-inch valve, then your CV would be, let me do this, okay, 1 inch and another 1 inch, then this would be your CV. So in 3/4, if you're selecting 1 inch, if the line size is 1 inch, if you're selecting 3/4, you've got options of 51, which is 3/4 to 3/4. If the line size was 3/4 and 3/4, it will be 51 to what its true CV would be. As the line size is 1 inch, you will have a CV of 26.5 and not 51, even though the valve is actually sized for 51. So you got to make sure what is the line size, what is the valve size, and how much of the CV it gives you against the line size. This will be a true CV to which you will be uh, measuring your pressure drop across the valve. Hope you understand. I hope you understood all of this in this video. That was my last bit. I'll show you a globe valve which I have in handy, which you should see how the valve actually physically operates in the. So this is how a two-way globe valve looks like. So it has an inlet and an outlet as explained in the earlier video. As explained in the video earlier, so globe valves have plugs which you can see inside the valve which I'm turning right now. So the actuator holds onto it, turns to 90 degrees, which will bring the plug up, which gives you the flow. Once it rotates clockwise again, it pushes the plug down, which restricts the flow. This is how the globe valves work with actuators. To demonstrate you the flow, I'm using the light instead of water, which I cannot use, of course, for obvious reasons. So once I pull up the plug, you should see the light rays coming out, and you should see the light rays go out when the plug comes down. As you can see the light rays coming out. That is how the flow is.
Thank you for watching my video. Like, share and subscribe, and hang out for new videos to come. Thank you.